Hi everyone, Eric here. Today I got a request from a student to do a certain problem. So we're going to do one of these Newton's laws of universal gravitation problems in chapter 6, specifically number 15. And this one states, at what distance from the Earth will a spacecraft traveling directly from the Earth to the Moon experience zero net force because the Earth and Moon pull with equal and opposite forces? So what this problem is telling us to do is if we were to launch a satellite or a rocket from the Earth and have it travel to the moon, the gravity from Earth's pull, the gravity from Earth and the gravity from the moon will eventually cancel out at some point, and there will be some equilibrium, and we have to find that point. Um, so there's going to be some vector from the from the rocket to the Earth that points that way, and then some vector from the rocket to the moon, and they should be equal and opposite. Um, the the thing here to realize is that this point isn't going to be just directly in the middle because the Earth and the moon have different masses. So if we think about it really logically, since the Earth is a bigger mass, this object has to be farther away from Earth and closer to the moon for it to feel an equal and opposite force. So the problem here is that we don't know the distances are between the two, as we will see. So the equation we're going to use to solve this is going to be, we're going to start with Newton's second law, and we're going to also need to know the force equation, force of gravity equation, which is G m1 m2 over r squared. And then I wrote down the radius from the Earth to the Moon. So we're going to need to know this distance here from the Earth to the Moon. And that's what I'm going to call D. And then we're going to need to know the mass of the Earth, and we're going to need to know the mass of the Moon. All right, so to solve this problem, usually the way I start is first I draw my forces, which I've already done. I'm going to have a force to the left and a force to the right. They should be equal to opposite. The next thing I do is I'm going to write my force equation, F equals ma. So F equals ma. And really it's the net force. So the sum of forces is equal to mass times acceleration. And then this problem tells you that it will experience zero net force. So I can set the sum of forces equal to zero. Now all I have to do is expand my sum of forces. So I'm gonna need to use now my force of gravity. So G times mass 1, which is the mass of the Earth, and then mass of Moon over this distance. Actually, this is going to be the mass of my object because it's this force from here to here, which is going to be my Earth to my object. So I'm going to call this mass of object over R1 squared. I'm going to call the distance from the Earth to my object from here to here. Call this R1. And then while we're at it, we'll call this R2. And then since this force points to the left, it picks up a minus sign. So that plus G mass of Moon, mass of object over that distance, R2 squared equals 0. Okay, cool. Now the next thing I can do is solve or set these two forces equal to each other. So just move this term over to the right side and I'll get G mass of Moon, mass of object over R2 squared equals G mass of Earth, mass of object over R1 squared. All right. Now we can see from here that the mass of the objects should cancel. My G should cancel. So what I'm left with is mass of moon over R2 squared equals mass of Earth over R1 squared. And then the issue here is that we have two unknowns, right? So R2 and R1 are two unknowns. We don't know either of those values. That implies that we need a third equation, which is why we have this distance from the Earth to the moon. Because now we can write our distance, Earth to moon, is going to be equal to this distance R1 plus R2. So D from Earth to moon is equal to R1 plus R2. And now I know this distance from the Earth to the moon, so I can write one of these R's in terms of the distance and the other R. Let's pick R2 because why not? So R2 equals distance minus R1. And then we can plug this term into here. And what we get is mass of the moon divided by D minus R1 squared equals mass of Earth over R1 squared. All right, so at this point, it's basically just an algebra problem. We've done all the physics now, and we just need to solve for R1. And now that if we do that, we'll have our answer. So let's solve for R1. It's a little tricky. I had to practice first before I did this, but the trick here is just to take the square root of both sides. So I get the square root of m of mass of moon over d minus r1 equals square root of mass of Earth over r1. Cool. And then from here, what can I do? I can say that I can put the R1, this R1 over here, this, yeah, I'm getting a little mixed up. Yeah, I can flip the R1s and M's, right? Yeah, okay. So I can flip this thing. So flip this around, and I get D minus R1 over square root M, mass of moon, equals R1 over square root mass of Earth. Cool. Then I can separate this D minus R1 over MM into D over square root mass of moon minus R1 over square root mass of moon. This is equal to R1 over mass of Earth. Cool. Now I can get my R1s on the same side. So yeah, just bear with me. It's just a lot of math. What I should get is D over square root mass of moon equals R1 over square root mass of Earth minus R1 over mass of moon square root. All right, cool. Now I can factor out an R1, and I get R1 times 1 over square root mass of Earth minus 1 over square root mass of moon. Still equal to D here. All right, now I find common denominators. Last time I screwed up the sign. Did I screw up the sign again? Yeah, I did. So this should be added. This should be a positive here. We add both of them together. So this is positive. Cool. Glad I caught myself. All right. So, okay, now we find a common denominator. Mass of Earth times mass of moon in the bottom, mass of Earth plus mass of Moon in top. So we're going to get square root mass of Moon plus square root mass of the Earth over square root mass of Earth square root mass of Moon. This is still equal to D over square root mass of Moon, in case we've forgotten. And then there's an R here still, R1. Then we flip this term onto this side, and then flip this term on both sides, or multiply the reciprocal of this guy, is basically what I'm trying to say. So we'll get R1 equals D square root mass of Earth times square root mass of Moon over square root mass of Moon plus square root mass of Earth. Okay. And then there's still this D is over mass of Moon here. Square root mass of Moon. Yep. Now this cancels and this cancels, and then I get something clean. D equals square root mass of Earth over square root mass of Moon plus square root mass of Earth. And that's equal to R1. Okay, cool. So, like I said, it turned into a math problem after you do all of that. But now I can substitute. I can substitute in my distance, 3.84 times 10 to the 6th into here. And I can substitute my mass of Earth, 5.98 times 10 to the 24, into here and here. And then substitute my mass of the Moon, 7.35 times 10 to the 22nd, into here. And then I can get the distance, R1, so from the Earth to the Moon, or Earth to the point. And then if I wanted to find R2, all I have to do is sub in what I get for R1 into this problem. So have a term for R1 here. We know this distance, solve for R2. I went a little fast because this Go board now has a time limit. So sorry about that. And this is also my second take. So I didn't want to get cut off halfway through. So I zoomed through it. But the beauty of the internet age is that you can pause and you can rewind and rewatch. And then if anything didn't make sense, please send me a message. But I hope that makes it clearer, this kind of problem clearer. And good luck out there. We are still being quarantined. It's been about a month, a little more than a month. So I don't even know what day it is anymore. It's hard. But good luck to everyone. We're all in this together. So see you all and have a nice day.